Hello and welcome back. So last time we looked at estimation error and approximation error, and we saw how ERM, which is an empirical risk minimizer, actually has good estimation error properties. And then to deal with approximation error, we looked at structural risk minimizer, which can be achieved via regularization in practice. How that has good you know approximation error guarantees. At least I kind of alluded to the fact that it has good approximation error guarantees, and all of this happen when you have a H or a hypothesis class which has finite VC dimension, right? So, and you are learning from a finite VC dimension hypothesis class. Now, yes, we know the definition of VC dimension. This was this two-player game. One player chooses the data points, the other player labels, and then the first player has to demonstrate a hypothesis that correctly matches the labels for these data points that the player chose. And then, the maximum number of rounds this game goes on till player 1 has a winning strategy is the VC dimension. Yes, that is the important combinatorial parameter that determines learnability and what is called as packed learnable. I mean, whatever we have seen is called as packed learnable, which means probably approximately correct learnability and so on. But it's still not a very natural thing to think about, right? So, I mean, of course, when you do the analysis of uniform convergence and so on, it kind of pops out a little bit naturally, but still, is there a simpler way to understand when we can learn and when we cannot learn from data, right? So a simpler question would be to ask, how can I characterize learning in a way that is much more intuitive to understand? And for this, we take a slightly different viewpoint, and I just wanted to talk a bit about this so that it becomes something that one has to think about whenever they come across some machine learning algorithm. It might be good to think about it in this particular viewpoint, which is the viewpoint of sample compression, which is what we are going to see today. So, compression is a very generic term. So, you have some data and then you want to compress this data so that you can recover the data from this compressed information in some sense. Now, what has that got to do with learning? The intuitive idea is that if you are able to somehow compress things, then it means you will be able to learn from that right? So, I mean, philosophically, right? So it means, so whenever we learn a concept, it's not like we have to necessarily remember every detail. As long as we kind of remember the main core conceptual idea, then we will be able to generate whatever we want, whatever knowledge we want from storing the conceptual ideas in the head. So how can we make that formal was one of the questions that people asked back in the late 1980s, and that led to this idea of sample compression, which says the following, right? So again, let's say we are in the binary classification world where you have some training data. Let's call this x1 y1 till xn yn, where all xi is in xi can be in any domain, yi is 0 comma 1. It's a binary classification problem, and let's also assume, right? So for simplicity, I mean, for this setup, yi equals h of xi for some h in h, where the VC dimension of h is d. Okay. So what it means is that I have a bunch of data points and then their corresponding labels, they are labeled using some hypothesis in a bag of hypothesis, right? So, and the bag of hypothesis is script h, and I am picking one hypothesis from that, and then I am labeling all my data points x1 to xn using that. Now, this h itself is of VC dimension, some small d, let's assume that it's less than infinity for the moment. Yeah. So it's a finite VC dimension hypothesis class. So I want to kind of understand that saying that I'm learning from a finite VC dimension hypothesis class, what does it mean from a compression viewpoint? That's the question that I'm asking. And for this we'll say the following, that you have the data set, yes, right. So, and let's say I define this function which is a compression function, compression function. Now remember, S has all x1 y1 till xn yn, and then from this the compression function, when I apply to S, outputs a t. A t is just a subset of S, right. So t is a subset of S, and cardinality of t, let's say, is some k, right. So out of n data points, for now k is less than or equal to n. I mean, we ideally, compression means we want, we are picking a subset of points, right. So the compression function, given n is, let's say, 1000, you have 1000 points, and then this compression function, let's say, picks only 100 points out of it, or 10 points out of it, whatever that k is, right. So those many points are picked from this. But how should these points be, right? So, or what property should these points have, the compressed points have? Well, the compressed points should satisfy the following property, right. So now if I give t as input to a decompression routine or an algorithm, so that should output some h prime in h, right. So remember, all my data points x1 to xn are labeled using h, right. So from this data set, I am picking some small set of points, and then I am calling that t, and the compression function is picking that. Now the compression function, if it was a good compression function, then the property of this t should be such that using just these k points, I should apply a decompression function to these k points, so that I will get some classifier in my hypothesis bag, script h. Now what should be the property of this script h, such that script is so h prime, such that h prime has the property h prime of xi equals yi for all I. So let's think about this for a second. So what's happening here? So I have 1000 data points, let's say k is 10, which means that if I have a compression scheme of size 10, then that means that if you give me 1000 points, I'll be able to pick 10 points out of this 1000 points using my compression function. And now I'll only look at these 10 points. I mean, let's say I give you these 10 points, and you don't have access to all the 1000 points, you only have access to these 10 points. Now you know that I have applied this specific compression function to my data set. You don't know the data set, but let's say the compression function. Let's say both of us know the compression function, both of us know the hypothesis class from which some h was originally picked to label the data points. All that is known, but you don't know which h was used. Obviously you don't know that. You also don't know what are my data points. The only thing that I give you is, I give you 10 points from my 1000 points, and now that is all you see, and you look at those 10 points, and then you apply a decompression function to come up with some h prime in the hypothesis class h. Now that h prime should label correctly not just the 10 points that I gave you, but all the 1000 points that I have. 990 of those 1000 points you have not even seen, right? So, but still the h prime that you come up with should have the property that it should label all the 1000 points correctly. Now, what I am not asking for is anything outside these 1000 points. I mean, there are of course other points that my h, the h that I used to label my points, might disagree with the h prime that you have, right? So which means that I am not asking h and h prime to be the same same classifier or the same hypothesis from my bag. It could be different, but it has to agree on the 1000 points that I originally had, right. So, if such a compression and decompression scheme is available, then we would say we have a sample compression scheme of size k, right. So, if this is possible, then so this compression comma decompression routines, right. So, is a sample SCS, stands for sample compression scheme of size k. So, it is basically saying that the information about all the labels can be obtained by a small set of data points. That is precisely what it is saying, right. So, I will be able to compress the information about all these data points to only a small set of data points and give it to you, such that you can you can recover the labels for all the data points that I originally had. Now, let us look at an example to make this clear, to see if this is even possible. I mean, this sounds like magic. If it sounds like magic, let us see if it is even possible, and then we will talk a bit about what is the relation to learning, right. So, here is an example. Let's look at the hypothesis class that we already encountered in this course, the interval hypothesis class. So, this is HAB. If you remember, this has H interval, which has all HAB such that HAB of x equals positive if x is between a and b and 0 otherwise. That is my class, and so let us say I have a bunch of data points, so let us say there are some data points that I receive from this class, not necessarily equally spaced or anything. So, x belongs to R, right. So, of course, in this case, yeah, and let us say I use some H, right, to label all these. Let us say the H I use is this. This is my A and this is my B, and HAB belongs to H obviously, and that is what I have used to label, which means that how would I label these points? Well, I would label this 3 points as plus and everybody as minus. Now, this is the data set that I have, right. So, think of, maybe if I just call this x1, x2, x3, x4, x5, x6, x7, x8, x9, then how is my data set? The data set that I am actually seeing is the following, right. So, the data set S that I am seeing looks like this: x1 negative, x2 negative, x3 negative, x4 positive, x5 positive, x6 positive, and then I have 3 more, x7 negative, x8 negative, x9 negative, right. So, this is my S. This is what I see, right. So, now I am trying to see if there is a compression scheme, right. So, the compression scheme that I am going to come up with here is going to pick the following subset of points. It is going to pick x4 and x6, and I will give that to you, right. So, what I will give you is x4 plus x6 plus. Both of these are positives. I am just going to give these two to you, right. So, this is your T, right. So, T, which is a subset of S. In this case, the cardinality of T is just 2, cardinality of S in this case was 9. There are 9 data points, out of which I took 2. Now, what you are going to do is you are going to look at T, which is a subset of S. Let me write down T again, x4 plus x5 x6 plus, and now you want to do a decompression to come up with some hypothesis. Now, let us say H prime, and now I am going to say H prime is just this algorithm, the decompression algorithm is just going to look at these two and say H prime is x4 comma x6. Right. So, that is the classifier that I am outputting depends on T only, right. So, I do not know the other points, I am just looking at T, and now I am coming up with a classifier, and that classifier is x4 x6, that is the interval, right. So, which means that the classifier that I came up with is this classifier x4 x6, right. So, just to make sure we are on the same page here, right. So, the original H that was used to do the labeling was AB, which is in this region, this interval, but now the one that got reconstructed is only in this interval, right. So, that is point number 1. So, these are not the same, right. So, this is not same as HAB, but what is same is the following, right. So, what is same is H dash of xi, H dash x4 x6, right. So, of xi equals HAB of xi for all I. That is, does not matter whether I am using this tighter interval, orange interval, or the slightly less tighter interval AB, which was originally used to label these points. For these 9 points, I get exactly the same labels. Now, what was my compression scheme? My compression scheme was to look at where are those positive data points in my data set S, and then take the smallest positive data point and the largest positive data point, and there is a small and large because this is just one dimensional input. So, there is a natural ordering that I can take advantage of. I will take the smallest positive point and the largest positive point, and then only those 2 points I will send it to you. You have these 2 points along with its labels, of course, in this case positive, and now you know that I have chosen the smallest positive point and the largest positive point in my data set, which means that if I have an interval that tightly bounds the smallest and the largest positive points, then you are sure that everybody within that, if there was a data point within that in my data set, that had to be positive because of my choice of my compression algorithm. And if it is outside this, that has to be negative, because if there was a positive point outside this, then either my smallest or largest is contradicted. So, anything outside this should have been negative, and so I would match all your labels, right. So, without knowing what the data points are, right. So, I just need these 2 data points to come up with a hypothesis. It may not be the exact hypothesis that was used to label your points, but still it matches everything with respect to the data set that you have, right. So, which means then that what we are saying is the conclusion is maybe we will write it here, the conclusion is H interval has a sample compression scheme of size 2, right. Why is it 2? Because no matter how many data points I had, in this case I had 9, but even if I had 1,000,000 data points on the real line, all I need to pick and give you is the smallest point with label 1 plus 1 and the largest point with label plus 1, only 2 points, right. So, it does not depend on the original n data points that I have. I mean, the size of the sample compression scheme does not depend on n, it only depends, I mean it is in an absolute sense 2 in this case. So, this hypothesis class is said to have a sample compression scheme of size 2. Now, interestingly, no, interestingly, if you remember from our discussion of VC dimension, the VC dimension of H int was also 2, right. So, we will see, I mean, if this is a coincidence or otherwise, but I am just making an observation that if we have a sample compression size or scheme of size 2, it also happens that in this particular case the VC dimension is also 2. Okay, that's good. So let's look at one more example to see if the sample compression technique is indeed can be applied to other hypothesis classes. So here is one more example. Let us say we look at axis parallel rectangles this time. Now, if you remember axis parallel rectangles, this is HAPR as I called it, is just a set of all axis parallel rectangles such that H xi is plus 1 if xi is inside the rectangle and minus 1 otherwise, right. So, that was the hypothesis class in 2D, of course, and let us say now again I have a data set S from which I have, let us say, a lot of positive points and then a lot of negative points. Right. So, and I know that all of these were labeled using this rectangle, right. So, this was my H, right. So, this is my H belongs to HAPR. Now, can you come up with a compression and decompression scheme for this hypothesis class, right. So, which means that both of us know that we are playing in the hypothesis class of axis parallel rectangles. You know that there is some axis parallel rectangle that has labeled all my data points. Now, but you do not know what the data points are, of course. I have to give you some data points such that both of us know how I am giving them, right. So, the algorithm is known, the data set is not known, but the algorithm is known, and now you have to look at these data points and construct an axis parallel rectangle which will work for all my data points. Work meaning the labeling that your rectangle gives correctly classifies all the data points that I have, but I cannot give you all the data points. Of course, if I give you all the data points, you can construct this rectangle, but without giving all the data points, can you still construct a rectangle which is correct with respect to all the labelings? Well, pause and think, it is not too hard, right. So, for in this particular case, the points that I would give, right. So, my compression scheme after compression would just pick let us say these 4 points, right. So, I am just going to give you these 4 points and then you only look at these 4 points, right. So, you do not have access to the entire data set, you only have access to this 4 points and that is your T, right. So, T, which is a subset of S, in this case the cardinality of T is 4 because I have given you 4 data points. And now what would be the rectangle, axis parallel rectangle that you would come up with by just looking at these 4 points? Well, that would be your decompression routine, and that is not too hard to guess, right. So, the decompression routine would give me some H prime, which would just be if these were the 4 points again, which would be the rectangle. Well, I would just pick the tightest rectangle that covers these 4 points, because I know this is kind of a extension or a generalization of my one dimensional interval that we saw, the interval hypothesis class, which means that I will come up with this tightest hypothesis class, right. Right. So, which means that all the 4 points that were given are right on the boundary. Of course, there might be examples of data sets where there may not be 4 points on the boundary, right. So, there may be only 2 points on the boundary, right. So, just to give an example, right. So, maybe I have 2 pluses here and then these are all pluses, maybe minuses are all here. So, I would then give you only these 2 and you can still construct a data set out of a rectangle out of this, right. So, what I am saying is that 4 is the maximum, you do not need more than 4. If you have even smaller compression scheme, well, you are lucky, you got lucky with respect to your data set, not necessarily always, right. So, if I had to generate an adversarial data set, then probably I would not give you something that has a smaller sample compression scheme, but then no matter how I give you a rectangle and the data points, you still can choose 4 data points, at max 4 data points, so that I can reconstruct a rectangle which will be of course correct for all the data points that originally were there in the data set S. So, this means that what does this imply? This implies HAPR, the axis parallel rectangle, has a sample compression scheme SCS of what size? Of size 4, right. So, again interestingly VC dimension of HAPR we already proved is 4. We argued last time, couple of lectures back, that this is also 4. So, then the interesting question is, well, can I understand hypothesis classes in a simpler fashion than using VC dimension? Of course, VC dimension characterizes something about a hypothesis class, but sample compression seems to be a much more intuitive way to understand learning, right. So, what do I mean by this, right? So, what do I mean by this is the following. I mean, there are results which show that if H has a sample compression scheme of size D, then we can argue that VC dimension of H is some order of D. And we know if VC dimension of H is finite, then this means that H is learnable. Learnable means the generalization error, estimation error, those kind of properties that we already saw go to 0 as n becomes larger and larger. The other question, the other side, I mean, this is already a known result, I am not going to prove this, but the other side is a very interesting question, which is, if I know the VC dimension of H is T, then does it imply, right? So, H has a sample compression scheme of size D, or order of T is also okay, right. So, what does this mean? This means that in the first part we are saying, if I can compress my data when it is labeled from a hypothesis from a when it is labeled using some H, then compression implies VC dimension, small VC dimension implies learnability, which means compression implies learnability. Now, I am asking the other way around, right. So, if the VC dimension is small, which means that if I want to understand a hypothesis class, one restriction I can say is that, well, the VC dimension is T, right. So, that's a usual restriction that people put on hypothesis classes. Now, if the VC dimension is finite, then does it mean that there is necessarily a compression scheme of size D? Well, I could have started saying VC dimension of H interval is 2. Now, there is a sample compression scheme of size 2 for this class. Now, VC dimension of H axis parallel rectangle is 4. There is a sample compression scheme of size 4 for this. These are 2 examples, and these suggest that maybe in general this is a true fact, right. So, if the VC dimension of a hypothesis class is D, then it means that it has a sample compression scheme of size D. Why is this useful? Is because though we saw VC dimension implies learnability, interestingly the other way is also true, right? So learnability implies VC dimension, right? So that's why VC dimension is such a fundamental parameter in statistical learning theory. We did not see this, and I mean in statistical learning theory you might see this, you would see this. Now VC dimension characterizes learnability. Finite VC dimension implies learnability implies finite VC dimension. Now we are asking, well, can I say finite sample complexity scheme, sample compression scheme, not sample complexity, sample compression scheme, does it imply learnability, and does learnability imply finite sample compression scheme? One way is true, which is if there is a sample compression scheme which is small size, then the hypothesis class is learnable because the VC dimension is small and so the hypothesis class is learnable. But then we are asking the other way around. If I know that the class is learnable, then I know VC dimension is small. We didn't prove that, but that is true. But if VC dimension is small, doesn't necessarily, we don't know if it implies there is a small sample compression scheme. Which means that if it is true, if true, then this means that I can think of learnability as compression. Learnability and compression are equivalent notions in this precise sense, right? So if I can learn from a class H, then it means that I'll be able to compress that class well in a sample compression sense, which means that the whole machine learning viewpoint is just a sample compression viewpoint, right? So the better I can compress, the better I can learn, right? So that's a much easier thing to say, and that's much more intellectually satisfying, so to say, in some sense, right? So than saying learnability means this complicated combinatorial parameter called VC dimension is finite. That doesn't feel that intuitive than saying learnability means compression. So the big question, and this is not, as far as I understand, this is not answered completely, right? So if the VC dimension of H is D, then does it have a sample compression scheme of size D? We don't know the answer to this question as of today, as far as my knowledge is true, as far as my knowledge goes, and this is called the sample compression conjecture, right? So that is, if I give you an arbitrary hypothesis class of VC dimension D, can you construct a sample compression scheme of size D, of size exactly D, right? So because that seems to be the case for all the examples that we have seen so far, right? So this conjecture, as far as I know, has been open for around 35 years now, or more than that, and this would, I mean, proving this would, I think proving this also carries a $500 prize by, if I am not wrong, by Professor Warmuth. Nevertheless, this is an important thing to understand, because it would then say learnability and compression are equivalent notions. So this is one other lens that I just wanted to give you, perspective that I wanted to give you to understand statistical learning theory. So this is the idea of sample compression. So next time we will see a different viewpoint. Until then, thank you.